Right. So I think the things we did with momentum transfer, if we have if we have few assignments, few quizzes, and then discussion after that, I think hopefully that's gonna be better for you to give you more understanding about that one. Right. For the EduNext, so we're in week 13. In here, I just put the slides and also diffusions. This is a video that we're gonna watch in a minute. And then the next week we have equation of change for the mass transport, and also week 15 is practices. But because we don't have 2 times 2 hours for lecture, I think we will miss some lectures and also practices. Okay, so check your timetable, check your schedule, and then let me know when you think you can have 2 times 2 hours lecture with me. Okay, yeah, just let me know. Right. Okay, any questions so far regarding the exam or regarding the additional class?
Bu, I have a question.
Yes.
So from the results that you showed before, so how do you know if we passed syarat lulus 1 and 2?
Okay. Yes. Right. I need to check up to which part. Yeah, it hasn't been finalized. Yeah, good question. I'll let the team teaching now. Okay, I will get back to you. Right. How about the others? Any other questions? No. All right. If there's not a question, let's open this session so we can learn about mass transport. Before that, let's watch a video first about diffusion. So at least we know what we're thinking about. We know what we're talking about, and then yes, just have a look at this one.
Water vapor spreads out into the atmosphere. It's carried by the wind, but it can also spread out of its own accord by a process known as diffusion. Invisible gases behave in the same way. The particles in a gas move randomly in all directions. This helps explain why a gas diffuses from one place to another. You can see diffusion happening on a small scale in the lab using bromine, an orange-coloured gas. Place a jar of air on top of the bromine, and it slowly starts to spread. It's moving up the tube against gravity. Over time, the two gases mix. After half an hour, both containers have a uniform colour. It takes time because the air and the bromine molecules are colliding with themselves and each other. So what would happen if there was no air for the bromine to bump into? All the air has been removed from this apparatus, apart from the flask containing bromine, which is isolated by a tap. Open the tap, and it spreads immediately. Watch again. In a vacuum, there's no air to collide with. The bromine diffuses much faster. See how slow the diffusion is when the flask is now full of air. It takes several minutes to get just this far. This simple setup can be used to compare the rate at which different gases diffuse into air. Nitrogen dioxide gas on the left is similar in colour to bromine on the right, but bromine molecules are much heavier. The lighter nitrogen dioxide diffuses more quickly. We can also compare the diffusion rates of other gases. Ammonia and hydrogen chloride gas are colourless, but when they meet, a white cloud of ammonium chloride forms. A piece of cotton wool soaked in concentrated ammonia solution provides ammonia gas. Concentrated hydrochloric acid provides hydrogen chloride gas. Place the two pieces of cotton wool at opposite ends of a tube and the gases spread out. You can compare the speed at which they approach each other by looking out for a cloud of ammonium chloride. After less than a minute, a white ring begins to form, marking where the gases meet. The white solid is closer to the hydrogen chloride end of the tube, on the right. So which gas has travelled faster? Another way of monitoring the progress of the gases is to run a piece of damp indicator paper along the tube. Hydrogen chloride gas turns it red, ammonia turns it blue. Why does ammonia travel faster? Diffusion also happens in liquids. Drop potassium permanganate crystals into water and they begin to dissolve. The purple solution then spreads out. It diffuses through the water. These three tubes containing water are immersed in baths at different temperatures: 0, 20 and 70 degrees Celsius. A crystal of potassium permanganate is placed in each. After 10 minutes, diffusion in the hot water is almost complete. Why does the rate of diffusion appear to be quicker at higher temperatures? What other factors might be involved?
Okay, so that is the video. So at least we know what we're gonna talk about. So today we're gonna talk about diffusions. Okay, so at least we know that later on. Wait, need to open. Okay, we'll open the PPT. So at least from that video, we know that there's a diffusion in gas and also a diffusion in liquid. Even there is a diffusion in solids. Okay, so basically the diffusion in a gas is much faster compared to diffusion in the liquid, and also diffusion in liquid is also much faster compared to the diffusion of solids. Okay, let me open the PPT first. And also we learned that diffusion would be a function of temperature. So the coefficients is called coefficients of diffusivity. Yeah. Wait, it's still verifying the Microsoft PowerPoint. Okay. Right. So wait, we can use slideshow. So now we're talking about the mass transfer or mass transport, and then it is in page. Yeah, you can check in the BERT. There's a section for mass transport. Okay, so just imagine we have two components. For example, the first component is the bromide gas, yeah, bromida, the bromide gas, and the second one is air. Air also is a gas, okay, and then we put it in some similar system in one place, and then they will collide with each other, right? And then after a while, and then we can see where they are readily mixed, and then also we can see also even what is the influence, if it is in atmospheric pressure or is it in a vacuum pressure. Okay, so so in here what we're gonna learn in mass transfer is all about the model. So we're just gonna model there is two components, component A and component B. Sometimes it can be more than two components, can be 3 or 4 or 5. Okay, but however the multi-components, it will not be discussed in this transfer panel course. Yeah, so we're gonna just focus on the binary components A and B. Okay, so first we have to just start again about the concentration definition. Okay, so the concentration definition is actually the amount of the component I and then divided by the volume. Okay, so the amount of the component I, so we have two I, which is there is a component A and also there's component B. Okay, just you can change this with A and B. Okay, so the concentration is actually the amount of concentration, the amount of A divided by the volume. Okay, and we have two types of concentration. There is a concentration based on the mass, which is the mass concentration of I. We know it is as a density, okay, or rho, yeah, rho I. Okay, so the density is actually, we know that density is mass divided by the volume, right? So we can say that this rho I is actually the mass of the I divided by the volume. So we know that rho is actually the mass divided by the volume. So similar with what you learn in, I think in absorption, in extraction, or in distillation, we need to use the same basis. If you use the basis or for the mass basis, then you need to use the mass concentration. If you talk about the molar basis, then you need to use the second term, which is called a molar concentration of I. Okay, for the molar concentration, you know that the molar concentration is the amount of I per mixture of volume, where the C is actually the mole of I. Yeah, so it would be the mole of the compounds divided by the volume. Yeah, we know already. So the difference between the rho I and also the C. Okay, so if we have a binary mixture, we will have a component A and B, let's say, so we can calculate how much is the rho A, which is the density or the mass concentration of A and also the density of B, or the mass concentration of B. Or if we divide them with the molecular weight of each component, we also can change this into a molar concentration, Ca and Cb. Okay, so all right, I hope up to here it is quite familiar for you, of course. Okay, so yeah, for example, if we have the density of air, so let's say the density of air is let's say 1 kilogram of cubic meter. Okay, and then you can also calculate how much is the density of oxygen in the air, and also let's say there is only nitrogen. You can also calculate how much that one there. Okay, just to do assumption, let's say we have 21% of oxygen and 79% of nitrogen. So if you want to calculate how much is the raw of oxygen, so that would be let's say 0.21 kilogram per cubic meter, and this one is 0.79 kilogram over cubic meter as well. Yeah, so at least and maybe you can call this is as row A, this is row B. Okay, if you want to change to the concentration, what you need to do, you can divide the mass with the molecular weight or the atomic weight, yeah, based on that, and divide by the volume, so that becomes the concentration. Okay, so the next one is the fraction. Okay, so the fraction, it is in a percent. So is for the binary components, we can also for the mass basis, the mass fraction is called omega A and omega B. While for mole fraction is also you know already that it is defined as XA and XB. Okay. So that is the we didn't differentiate. Yeah, we just put it XA and XB just to assume that it is liquid. Okay, but we know also that in a gas phase, or if the system involves two phase, gas and the liquid phase, like in absorption, you know that YA and YB is term for mole fraction in the gas phase, and XA and XB is the mole fraction in the liquid phase. Yeah, you know that one. But for this one, because it's only one phase, let's just call the mole fraction is the XA and XB. Okay, so we in the term of mass unit, in the term of the basis of the mass, we know that the fraction of A and also the mass fraction of A and the mass fraction of B, if we add it together, it would be equal to 1. Okay, so for example, we have the mass fraction of nitrogen, let's say 0.79, the mass fraction of oxygen is 0.21, and then add them together, it's become 1. Just ignore the CO2 and argon and so on. Yeah, just let's say okay, so the sum of them is 1. This also this one, the density or the mass concentration of A multiplied with the mass concentration of B, it would be equal to rho. Okay. So and then after that, this one here in molar unit, we also know that the mole fraction of A plus mole fraction of B would be equal to 1, while the concentration, molar concentration of A plus molar concentration of B would be equal to the concentration of itself. Okay, so this is a good basis to learn about the mass unit, so you don't confuse later on in the next formula. Right, so let's just get talk about the laws. Okay, so in the momentum you have Newton's law, and heat transfer, or in the energy transfer you have Fourier's law. And now in this one, in the mass transport, you have Fick's law. Okay, so the Fick's law is actually describe the quantification of the mass transfer component in the mixture. Okay, and then the rate of the mass transfer of the components would be corresponds to the driving force, which is the concentration gradient, and also reverse to its distance. Okay, so if you think about it, for example, for the momentum tau yx equal to minus mu dvx dy, right? So, or if we talk about the heat transfer q, x, let's say, would be minus k dt dx. Or now here we're gonna this one is actually it's called the this also called the resistance. Okay, and this called, or this one here is called driving force. So in momentum, we know the driving force is the difference of the velocity, right? In the heat transfer, the driving force is the difference in the temperature, okay, and also reverse of its distance. And then now later on is the flux for the Fick's law. This is called J minus d dc I divided by dx, let's say. Now this gonna be the driving force, which is the gonna be the concentration. Okay, so for mass, the driving force is the concentration. Just remember just the video that we watched a while ago, where we have this tube like that, like a ball there, and then they have a tap over here, and then they have the bromine gas, right? This one is vacuum. So in the vacuum there is no air, there is no other gases. So the concentration, or the, let's say, the rho is going to be very small, right? Or the concentration molar, let's say. Well, here the concentration is a very high. Okay, so when you open the tap, what happens is there is a very large driving force in the bromine gas over here with the vacuum over there. So that's why the rate of the mass flux would be very fast. Okay, another one, if we have that one, yeah, the another one, the second one, if we have the bromine gas here, but we have air as well, so this also has the concentration. Yeah, you have some things there. So the concentration here to here is not very in terms of bromine, it is high, but in terms of we also collide with air over here. So that's why the rate or the driving force is not as fast, or not as large as the vacuum one. Okay, right. Okay, so this is called why I want to explain this one, because this is analogy for any transfer phenomena that we observe in the nature, even for the momentum transfer, or perpindahan gerak, or heat transfer perpindahan panas, or mass transfer perpindahan massa. This always resistance multiply with the driving force, and also it's gonna be reversed to its distance. Okay, so Yeah, so here we can see that for the flux A, let's say the component is also similar to component B. If you want to write the formula with respect to component B, if we write the flux in a mass, we call it JA. Okay, so the small j is actually for mass. Okay, so what I write over here is for capital, so it is for a molar basis, mole basis. In here we have the first one in the term of mass and also in the term of mole. Okay, so here we can have the JA, or the mass flux. Yeah, the mass flux. So what is mass flux? The mass flux is actually something's divided by area. Okay, so okay, let's say I have just say I have a glass here. So if you want to say what is the mass flux, let's say on here, so this is gonna be the area. So it should be divided by the area. Right. So here the mass flux is actually would be corresponds to the driving force, which is the delta of the rho A in one place and the other place. Okay, in the final and the initial one, and then divide by the distance, right? Or because we know that the rho A is actually the rho divided by multiply with the mass fraction, we can also write it would be the rho of the mixture, and then multiply with the delta of the the mass fraction. Okay, or if we write the flux in moles, which is the JA, or the capital JA, would be corresponds to the delta in CA and also the delta Z, or the concentration of the mixture, right? The concentration of the mixture, and then multiply with the delta of XA. Okay, so the one that is constant here, which is used as the resistance, is called the DAB, or the diffusivity of coefficient. So I need to write the DAB over here. So let's say this is the A. Okay, so JA would be the resistance. Okay, and then this is the mu, this is the K for the heat flux, phase transfer, and this is the mass, the DAB. Where DAB is called diffusivity coefficient. Okay. Remember the one that we watch, we have a cotton full of ammonia, and the one is the cotton of hydrochloric acid, right? Why ammonia is travel faster compared to the hydrochloric acid, and this here they would form the ammonium chloride, right? Because the ammonia has diffusivity coefficients higher compared to the self diffusivity components, higher compared to this one. Okay, so if you want to know the diffusive coefficients, you can see the books, and then for example, how to calculate this. There is some empirical correlation, there are some formula to do that, but we're not gonna talk about that in this course. Yeah, usually the DAB would be just given in the problems. Okay, but if you, let's say you have a final project, or you have a problem solving a case, let's say about mass transfer, or you need to do some modeling about the mass transfer, you can predict the diffusivity coefficients and also in that media. Okay, so that there's some list how to predict the diffusivity coefficients, and we also know that the diffusivity coefficients is also a function of temperature. Let's say you see that the potassium permanganate in the video, the purple ones in the water, you can see that why it can diffuse so quickly on hot water compared to on ice water, of course, because the diffusivity coefficient at higher temperature is much higher compared to diffusivity coefficient at lower temperature. Okay, the easiest way to know diffusivity coefficients is by if you put if you have a glass of water and then you put just a piece, maybe just a spoonful of sugar in hot water and a spoonful of sugar in the cold water again, and wait maybe 5 minutes, and then you can have a sip later on after buka puasa maybe. And then which one is sweeter? I'm sure that the hot one would be much sweeter, even if you don't stir them, yeah, tidak diaduk. Okay, even if you don't stir them, the water will taste sweeter because there would be a diffusion, and that diffusion is called molecular diffusion. It just diffused by the molecular ones because of they have their own diffusivity coefficients. Okay, so there you go. So this is the fixed law number 1, hukum fix 1. We call it, why? Because we will have another one, the second law fix, fix number 2. So in the fixed law, JA equal to minus DAB d rho A over dz. The negative here because we always calculate the delta from the final minus initial, where the final one usually they have lower concentration compared to the first one, right? So then to make the rate is positive, then we put negative here, right? Okay, so this tells you the rate transfer of component A in molecular with a stationary medium, dalam medium diam. Okay, so imagine that it just because of the molecular, because of all the molecules, even in a gas, in a solid, or in a liquid, the molecule always moving. Okay, dia akan bergetar, ya. They will always moving, and then because of there's a driving force, of course they will move into the to the final direction, into the equilibrium, right? And then the fixed law, the number 1, shows you the rate transfer component in a molecular one. Okay, the thing is, so that means if I know my diffusivity coefficients, I know the height, for example, I know the height of my tube, for example, I know the difference of concentration, I can calculate the J. Okay, for example, in that the previous experiment in the video, we know the bromine gas, the concentration at the bottom, we know the height of the we know the height of the what's called the tube, yeah, the tube, and then we know the diffusivity coefficient of the bromine in the air. Then you can calculate how much is the rate, okay, or how, when, or maybe later on the time when you can get the the mixture, yeah, the complete mixture. Now the thing is, when you put the spoonful of sugar on the water, right, and then you just wait, okay, it's gonna take a long time, right? And then you don't have much time to do that. You just want to drink the coffee with sugar. So what you do? What you do to speed up the process?
Stir with spoon, Bu.
Yeah, you stir it with a spoon. Okay, of course, if you want to make it faster, you want to stir it with the spoon. And the stir it with the spoon, it is actually it turns like a convective way in a heat transfer. Okay, so when you stir it with the spoon, you include a velocity on that. You create the vortex on your glass. Okay, so see, you can learn a lot from a glass of coffee or a cappuccino there, right? Okay, so now we're gonna talk about the how if the mixture is also moving. Okay, how if also the mixture of the VA or the VB is also moving. Okay, so that is of course the rate would be increased, but how to quantify that one? Okay, so let's consider that in a mixture we have the first component A. The first component is moving with velocity of VA. Let's say we stir it, and then, or maybe we just put the flow like that, and then they have a velocity of VA, and the component B will also move with a velocity of B, right? And then also, you know, the velocity is a vector, yeah. Vector means they have a direction. They also have the quantity. Okay, the direction, arah, yeah, the direction, it can be similar, it can be different. Okay, maybe we can just push maybe in one way to here and one way to that one, or maybe in a similar direction like that. Okay, so later on we will have, we call it the average velocity of the mixture, velocity of the medium velocity, which is would be the average velocity of the VA and also VB. Okay, so let's just define that the average velocity, kecepatan rata-rata ya, the average velocity is actually the velocity of A multiplied with the concentration of A plus velocity of B multiplied with concentration of B divide the total concentration. Yeah, that's how you define the average velocity. And then let's define that there is a mass average velocity, which is V dash over there, and also molar average velocity with V star dash. Okay, so here then in so let's try one dimension transfer, satu arah perpindahan, and then at that that stationary basis, let's say we have the component A and B, the initial component, and also the component medium. Okay, and the component, the velocity of component A is actually the VI minus V, or VI minus V star. Okay. Okay, looks like this is 7 minutes to 9 o'clock, so I need to finish it now. But actually, just to make sure that the kecepatan komponen sebenarnya, the actual component, it's like when you have a train and you also walk. Okay, so you and the train, for example, this one is in 10 kilometer per hour, but you also walk, let's say, just 4 kilometer per hour. So if you want to know the actual components, the train would be the this one, yeah, the your actual component is actually the yourself. You walk from one satu gerbong ke gerbong lain ya. So in the train with 4 km per hour minus this one, which that is related to the one dimension. Anyway, later on we're gonna learn about the second one later on, but this one. But I think we need to find some more time. So we're gonna see you again next week on Wednesday again. But if you think you have some time next week to have more course with me, just let me know, yeah, Kevin. All right, it's almost 5 minutes to yeah, almost 10 minutes to 9 o'clock, so I really need to stop here. At least we know fixed law, yeah, one fixed law, and then we're gonna learn also the fixed law for the convective transport, like we say. Okay. All right, I think I need to stop it now. Thank you very much for your attention, and I'm gonna see you again next week. And also, if you have additional classes, let me know. Yeah. Okay. Bye bye.